Hi everyone, my name is Amith. I am presenting to you this submission for task 1 at the MICCAI 2022 Hackathon. The topic, which is very interesting, is called Domain Shifts Between Clinical Annotators. And I represent the University of Bern, and all of the analysis I've prepared is in this repository at the bottom of this page. So here's a brief overview of what I'm going to present today. We start with an introduction. We go through some experiments with histograms of annotations and disagreement scores. We then visualize these disagreements versus the uncertainty metrics that have already been provided in the code. And finally, we look at relationships between the lesion size and these disagreements. Is there a relationship in the first place? Concluding, we look at possible next steps and finally have some acknowledgements. I hope to run through all of this within the 5 to 7 minute timeline that we have. All right, so motivations for the experiments that we run. So I'll walk through this very quickly. So here's why we are doing this. The first motivation is to quantify the impact of annotator variance, particularly on this multiple sclerosis dataset of white matter lesions in the Shifts 2.0 publicly available dataset. The second motivation is how does the model uncertainty compare against annotator variance? And the underlying question is, how is annotator variance even quantified? The next question is, are there correlations between these uncertainty metrics, the model prediction accuracy, and lesion sizes? Personally, for me, I'm interested to know more about the community of researchers in this space and to network. And so I think it's a motivation in itself for me to be involved here. And also, this is reasonably close to my PhD research topic. So this is all the more interesting. Right, so here are some initial results for the first part of the experiments, which is understanding this annotator variance, agreements and disagreements. Okay, so here's one way of understanding what the level of agreement amongst annotators is for marking a voxel as a lesion or not. We have in this dataset 7 annotators. And what this histogram indicates is the ratio of the agreement for voxels with at least one annotator marking it as lesion. So if only one annotator marks that particular voxel as lesion, then it falls under the leftmost bin of 1 by 7. So this is unique annotator marks it as a lesion. If 2 annotators mark the same voxel as lesion, then that voxel falls under the second bin. 3 falls under the third bin, and so on. So the last bin here is where all 7 annotators have marked it as lesion. So that's full agreement, and 1 out of 7 is just a unique single annotator. The dice score that the model predicts for this case is 0.67, and I'll explain what lesion confidence is, which is something that I've tried to come up with to measure this agreement or not, and for this case it's 0.5057. Here's another subject, which is subject 4. Notice here that the lesion volume is smaller, it's only 2620 millimeter cube, and the entry for 1 out of 7 is the highest, which means that there is more disagreement between the annotators, and the dice score for this subject is 0.51, and this lesion confidence is lower now, is at 0.32. Here's an example of higher agreement where there are more voxels where all of the annotators agree with each other, and it looks like it also reflects in the dice score of the model, and the lesion confidence here is 0.59, which is again higher than the previous cases. Here's an interesting situation of an extremely small total lesion volume. So the total lesion volume, what I mean by that is if at least one annotator marks a voxel as lesion, then I consider it as part of the lesion volume. And so in this case, see that the lesion volume is 347 millimeter cube, very, very small compared to the others, which were 60,000, 2,000, and so on. And notice also that the prediction of the model is 0.15 in terms of dice. Our lesion confidence here is also lower, is 0.41. We'll come back to this later on as well. So now I look at how the model dice score relates to the total lesion volume. So subjects on the top right are better performing than the ones on the bottom left. So subject 19, 6, 1, 22 are better than 28, 18, and so on. Interestingly, even for small lesion volumes, let's say the one on the bottom right here, that's subject number 23, for example, the dice score is still very high. Again, the total lesion volume includes any voxel that any of the 7 annotators have indicated as lesion. So this is not majority vote, not staple, that's a superset. The question then is, can we build another metric to consider this annotation variance within these metrics? The correlation coefficient here between the dice score and this total lesion volume is 0.42. So here's a metric that I thought would be interesting called lesion confidence. So the idea is to take into account this histogram and compute the proportion of annotators agreeing that a voxel is a lesion and multiply that element-wise by the normalized histogram ratio here, thereby giving us a score that takes into account the agreement or not, right? And here is how this lesion confidence varies with the total lesion volume, and you can see it's a little more linear. There are no entries on the bottom right or the top left, for example. It separates these two cases, case 24 and 15, where 15 has much lesser agreement than 24, and so they are farther away from each other in the plot on the left here as compared to the previous slide. The correlation coefficient is also higher between this lesion score or lesion confidence and the volume itself. Next, we look at visualizing annotator disagreements versus these existing metrics. So thanks to the discussion in the Discord chat, here is how we compute this disagreement variance. So from the evaluation set in the MSSEG dataset, we average all of these voxel-wise annotation masks, and then we compute p times 1 minus p, where p is the value of the voxel. So this leads to an unbiased measure of the variance, where 0 means there is no variance or there is no confusion, certainly foreground or background, and 0.25 is the worst case scenario. So the provided code already generates uncertainty estimates using some of these methods here, and we'll compare these with this disagreement variance that we have now computed. Here's a screenshot of the visual verification of this location correspondence. The leftmost plot is the disagreement of a particular slice. The middle plot is this metric, particularly the expectation of entropy. And the rightmost plot is the ground truth, which I believe is majority vote used for training. And you can see there are sort of locational correspondences. I have like videos for all these slices here where you can see the correspondence even better, and the link for that is here below. The challenge with this, though, is that these scales for these metrics vary. So, for example, this one is the confidence metric, and the scale for it is, as you can see, inverted and very different. And so it's difficult to quantitatively compare all of these three, or at least the first two on the left. So here are some challenges with coming up with quantitative measurements. So the scales are different for different metrics. The scales for the disagreement is also between 0 and 0.25, so need to normalize. And so what we do is to rescale these metrics and the disagreement volumes to between 0 and 1, and then do a simple MAE or MSC to measure which metric is the closest to the annotator disagreement, and if it's consistent across subjects. So here are some quantitative comparison results. So each of the columns here are different metrics that were already provided by the code in the repository, and the numbers here are the mean square error and the mean absolute error between the disagreement volume, which is rescaled, and the metric volume. And as you can see here, the expected entropy measure is the closest for both of these metrics. To be honest, I haven't really delved deep into what each of these metrics mean, and so maybe when it's not a weekend, I'll look further and find out if this even makes sense. Next, I'm looking at how lesion size matters, if at all, for annotator disagreement. So this is a quick and dirty analysis on that. So here's how this is computed. We use this disagreement volume that we created earlier, and we do a connected component analysis and separate each region, threshold it for volumes greater than 9 voxels. For each of these volumes, we then compute the average disagreement values within this region only, and then plot this versus the size of these volumes. The expectation is that the annotators would find hard to segment smaller regions, and hence there could be more disagreement there, and larger regions could have lesser disagreement or more agreement. Here's an example of a result for subject number 1. As you can see, there's one dominant lesion that's really large, and so what we have to do then is filter out these large lesions as well to see the trends in these smaller regions. After filtering the large regions, here's how the variations look. The expectation of a negative trend doesn't appear to be true. Also, there isn't really any relation, it appears, to sizes of lesions and the disagreement within that region. How do other subjects look? Here's another subject where there are fewer independent regions, and also that same trend kind of seems to be true here. What you can also see is there are many small values of the disagreement for a range of different volumes of these lesions, and so again it kind of points to not much of a relation between the size and the disagreement. So more investigation, I think, needs to be done here. Here's another example of there being no correlation between these two kind of variables. This could be due to multiple factors. I think the estimate of disagreement may not be the best. There could be other ways to evaluate this, and the large lesions could possibly bias this analysis. So maybe filtering more aggressively could be useful. Finally, coming back to this subject number 20, what you see here is this is a tricky case. There are only 3 lesion regions, in fact 4, because we filtered the largest, and the entire volume is also super small. So this points to probably there is something wrong in how the ground truth was generated for this particular subject. This is super out of distribution for the model, and hence the dice score is also probably very small, which is 0.15. So exploratory data analysis really helps to track these situations. What can we do next after the hackathon? Here is some more analysis that potentially could be done. Looking at better measures of disagreement. Is there other ways to be more accurate than just averaging? Can you rate one annotator higher than another, for example, by weighting them separately? What if we leave one of the annotators out and find out how the estimates change? Is that annotator too far away from the other 6, for example? Are there other ways to measure the model uncertainty that more closely matches this data uncertainty? And finally, looking at intra-center versus inter-center variation. So in this analysis at the moment, it's just intra-center, but inter-annotator. So maybe there's more to learn intra-center as well, inter-center as well. And finally, some acknowledgements. Many thanks to the organizers of the hackathon for the platform and the Discord chat. The Task 1 mentors who I've listed here for the code, the presentation, and all of the thoughts they shared. And finally, the Shifts project itself for sharing the data and analysis for us to run this analysis on. Thank you.